Great. Well, thank you very much for the introduction and for having me as well. It's very nice. So my talk is essentially going to be based on joint work with Kai Cieliebak, Oleg, Lazarev, and Agustin. And it's about studying some fairly interesting non-Weinstein Liouville domains in dimension 4. So, So maybe I'll just recall what a Liouville domain is. So it's a triple made of a compact manifold with boundary together with a symplectic form that is exact. And when you have one form lambda like this, you can dualize it through the symplectic form and get to what's called the Liouville vector field. And we want it to be positively transverse to the boundary, or alternatively, lambda restricted to the boundary is contact. And among these Liouville domains are very nice ones called Weinstein domains. And for those, there is an extra piece of data, which is a Morse-Lyapunov function for the Liouville vector field. And in particular, the Liouville vector field has very nice dynamical properties. So, I mean, on the left is the canonical picture of a Liouville domain. And such a domain can always be completed by adding a cylinder. I think we've seen that in the previous talk, to obtain what's called a Liouville manifold, finite time. And on the right, there is a poor depiction of a Weinstein handle. So these Weinstein domains can always be obtained by attaching what's called Weinstein handles. And those are handles of index at most half of the dimension of the manifold. And in particular, if you think about it, in dimensional analysis 4, a Weinstein domain always has a connected boundary. And in this handle, there is especially in the critical handles, so in the index n handles, there is a fairly interesting Lagrangian, which is the core of the handle, and this is a Lagrangian disk. And so a lot is known about Weinstein domains. They've been studied for a long time, but very few is known about non-Weinstein domains. And the first example was introduced by McDuff in '91, and it's relatively simple. You can start from a closed hyperbolic surface with a volume form sigma, and you can build a symplectic form on the cotangent bundle of sigma by just adding the canonical symplectic form and the pullback of this volume form. And here, the canonical symplectic form is in coordinates written like this, where the QIs are coordinates on sigma and the PIs are the dual coordinates, and pi is just the projection on the base. And there is some magic happening. If you remove the zero section, the symplectic form becomes exact, and it becomes a Liouville form. And if you remove a neighborhood of the zero section and a neighborhood of infinity, you will end up with a domain, a Liouville domain that looks like segment times the unit cotangent bundle of sigma. And well, this thing is obviously not Weinstein because it has this connected boundary. And if you look at the contact forms on these two boundaries, well, on one side, you will have the canonical contact form on S star of sigma. And on the other side, you will have a prequantization contact form because S star of sigma, it's a circle bundle over sigma. And it's a prequantization bundle for this volume form little sigma. Okay. So that's one example. And there is another example that I like. That was first written by McGuigas, I believe, in '95. And on R3, you can write down these two contact forms, very explicit, right? And then you can build a symplectic form in R4 in the following way, where S is the extra coordinate on R4. And it's fairly easy to check that gives you a symplectic form. But what we do like is to take compact quotients of R3 so that this lambda would descend to a Liouville form on something like R times a closed manifold. And to do that, well, you can pick your favorite hyperbolic matrix in SL2Z. You can diagonalize it, and this diagonal matrix acts very nicely on alpha plus and alpha minus. And actually, if you quotient R2 by not the standard lattice, but the lattice that you obtain by the image by this matrix P of the standard lattice, well, you will get a torus bundle over S1, whose monodromy is essentially given by A, and these alpha plus and alpha minus will descend to contact forms on this M. And then this lambda will give you a Liouville structure on R cross M. So similarly, this thing, well, you can chop R to get minus A times M for A sufficiently large, and that will give you a domain with disconnected boundaries as well. So those are two fairly explicit example of non-Weinstein Liouville domains, and there is a number of natural questions that we can ask. I mean, first of all, do they have closed exact Lagrangians? So those are Lagrangians, so that the Liouville form restricts to closed one form on the Lagrangian, or maybe closed weakly exact Lagrangians, where here we only require that the symplectic form on disks with boundaries on L is 0. And also maybe not interesting non-compact exact Lagrangians, which are cylindrical at infinity, meaning that the Liouville vector field is tangent to the Lagrangian at infinity. Okay, and so the first theorem that we have is, well, actually the McDuff domain, or its completion, McDuff manifold, has a lot of interesting Lagrangians, and we construct for every simple closed geodesic on the surface an exact Lagrangian torus that is well defined up to Lagrangian exact Lagrangian isotopy. We also get a family of non-exact but weakly exact tori in the same Lagrangian homotopy class of this T gamma. And we also get for any immersed oriented geodesic, we can look at the positive conormal lift in T star of sigma minus the 0 section, and that gives an exact Lagrangian cylinder. But so really the content of this theorem is the first two items. The third one is easier to get. And so I guess one way to think about it is this way. So here, these exact Lagrangian tori and weakly exact tori, they kind of look like what you would get if you look at gamma and you look at the fibers of T star sigma over gamma, and you take a circle in these fibers and you rotate it along gamma. But if you do that, you won't get a Lagrangian, so you have to modify this construction, and that can be done in such a way that this Lagrangian torus will project to a neighborhood of gamma. Not exactly gamma, but a neighborhood of gamma. And in particular, if you pick a collection of 3G minus 3 disjoint closed geodesics, that will give 3G minus 3 Lagrangian tori, which will be non-isotopic and disjoint as well. So a fairly large number of exact Lagrangian tori. And well, there is also a depiction of this positive conormal lift, which is an exact cylindrical Lagrangian. And in the torus bundle domain or manifold, situation is a bit different because there are no closed exact, say, orientable Lagrangians. But the T2 fibers are weakly exact Lagrangians. And moreover, if you take any periodic orbit of this matrix A, seen as a diffeomorphism of the torus, you can take the suspension of this finite saddle point that will give you a knot in M, the torus bundle, and then you can cross it with R and obtain an exact Lagrangian cylinder. So that's another depiction. We have this torus bundle over R cross S1. The fiber itself is weakly exact Lagrangian torus, but if you take this orbit O and you rotate it along the S1 direction and you take this cross R, that will give you an exact Lagrangian cylinder. Great. But both of these examples actually can be written as follows. We can write the Liouville form as this kind of exponential interpolation, which is alpha minus and alpha plus, where ES alpha plus is a symplectization of alpha plus, and E minus S alpha minus is the negative symplectization of alpha minus. So in some sense, we're gluing two symplectization together, but in the wrong way. And the Liouville vector field is in the kernel of both alpha plus and alpha minus. It's possible to do some computation and see that the skeleton is exactly at 0 cross M, and the Liouville vector field is tangent to this M0, and it restricts to a flow that is an Anosov flow. And this flow in the McDuff example, it's essentially the geodesic flow on sigma, and in this torus bundle is essentially the suspension of an Anosov diffeomorphism of the torus, which is a linear diffeomorphism of the torus. So that's a very schematic depiction of what's going on. On M0, the Liouville vector field is tangent, and then suddenly, if you move left or right, it starts becoming transverse to all the slices. Okay, so maybe let me tell you what the definition of an Anosov flow. So on a closed-oriented three-manifold, a non-singular flow generated by some vector field X is Anosov if there is some continuous invariant splitting of the tangent bundle into three pieces: the direction of the flow, a stable direction, and an unstable direction. So the stable direction is stable, meaning that if you apply the flow to a vector in this stable bundle, its length will decrease exponentially fast. And in the unstable, the length will increase exponentially fast. And this holds for some constant CNA, and also some auxiliary Riemannian metric. And then you can also add the direction of the flow with the stable or unstable direction to get the weak stable and weak unstable direction. And these two plane bundles integrate to some Todd foliations, the weak stable and weak unstable foliations. And I should also mention that these Anosov flows satisfy some structural stability. If you start with an Anosov flow and you wiggle it a little bit, then it's still going to be Anosov, and the two dynamical systems that you obtain are actually closely related. They are equivalent for a suitable notion of equivalence. And so that's the picture with these stable and unstable direction. And here I also picked some vectors spanning the stable and unstable directions. And the direction of the flow in blue is actually pointing towards okay. So this motivates the following definition. On a closed-oriented three-manifold, I will say that a Liouville structure is an Anosov Liouville structure if it's induced by a Liouville form of this type, where alpha plus and alpha minus are contact forms. The kernels are transverse contact structures. It's also called a bicontact structure. And the intersection is spanned by some Anosov vector field. Okay. And so let me also introduce some notations. I would write this curly AL, the space of these Anosov Liouville structures on R cross M, AF, the space of Anosov flows, but up to positive time parameterization, meaning that I only remember the direction of this flow and the orientation. So it's a one-dimensional oriented foliation or distribution. And there is an intersection map that very naturally associates an Anosov Liouville structure to an Anosov Liouville structure will give you the intersection of C minus and C plus, thought of as a one-dimensional oriented distribution. And so with these notations, I show that this map, this intersection map, is an acyclic self-vibration and also a homotopy equivalence, which means that it's a self-vibration, which is also a weak homotopy equivalence, and these spaces are very nice. They have the homotopy type of suitable complexes. So by Whitehead theorem, it's also a homotopy equivalence. And as a corollary, an Anosov flow on a three-manifold M will give you a Liouville structure on R cross M that is well-defined up to homotopy, and that only depends on the homotopy class of the Anosov flow, the homotopy class within the space of Anosov flows. And moreover, the symplectic invariants of this Liouville domain or Liouville manifold, like the symplectic cohomology of the wrapped Fukaya category, are invariants of this flow. So with this construction, we get potentially very interesting invariants of Anosov flows. Okay. So maybe before I give you the construction, maybe are there any questions? Okay, so no questions. And the construction follows from ideas of Mitsumatsu that were extended by Surina Hozuri, and it looks like this. So I had the splitting with the stable and unstable directions, and I can rotate the stable and unstable direction by 45 degrees and get these contact structures. But we need a bit more. We need also one form. So the weak stable and weak unstable foliations or distributions can be defined as the kernel of suitable one forms. These one forms will satisfy that if I take the Lie derivative along the flow, I'll get something that is proportional to these forms because of the integrability of the weak stable and weak unstable distributions. And I also want these constants Rs and Ru that I call the expansion rate of the Anosov flow to be as such. So the expansion rate in the stable direction is negative, meaning that the flow is contracting in the stable direction, but it's expanding in the unstable direction. And with these notations, then alpha plus and alpha minus defined as the sum of differences of alpha U and alpha S will give the contact forms that we need to define the Anosov Liouville structure. So that's the construction of such things. And it turns out that for this very general definition, we also get a lot of interesting Lagrangians. So any closed orbit of the Anosov flow will give a Legendrian for both contact structures C plus and C minus. And the cylinder over this lambda gives an exact, even strictly exact Lagrangian in R cross M. And well, this just follows from the expression of the Liouville form. And in particular, it's known that for Anosov flows, there are many, many simple closed orbits. And so we potentially get many, many interesting objects of the wrapped Fukaya category. And this construction also recovers the positive conormal lift of oriented closed geodesics in the McDuff domain, and also the cylinder, the suspension of these orbits of the matrix A in the torus bundle domain. So we always have these Lagrangians, and they naturally span the subcategory of the wrapped Fukaya category that we call the orbit category, because we can think about it as putting an A-infinity structure on the set of simple closed orbits of the Anosov flow. And now we can ask a number of questions. So what is the algebraic structure of this category? Maybe it's just trivial, it's unclear. And does it split generate the wrapped Fukaya category, meaning that, loosely speaking, we can recover the full wrapped Fukaya category algebraically from these smaller collection of objects. So the first thing to try when you have such a nice collection of Lagrangian is to try to apply what's called Abu-Zaid's criterion. And in that case, we are able to show that, well, this criterion fails, which means that the open-closed map from Hochschild homology of this orbit category to the symplectic cohomology of the manifold does not hit the unit. So Abu-Zaid's criterion says that if it hits the unit, then this W0 would split generate the wrapped Fukaya category, but here it fails. And moreover, this open-closed map has a non-trivial co-kernel and infinite rank kernel. And it's a theorem of Shield-Ganatra that says that when Abu-Zaid's criterion is satisfied, the open-closed map is an isomorphism, but here it's very far from being an isomorphism. So that's a bit sad, but it's life. And we can also show that this orbit category is actually a fairly big infinity category. And we can show that it's what I call maximally non-finally split generated, which is a complicated way of saying the following. If you take a subcategory of the orbit category, so you take a collection of these simple closed orbits, and you take an orbit that is not in this collection, then this object L is not going to be split generated by this collection A. So it's not possible to split generate an object from different objects. And this has a number of consequences. It implies that for two different simple closed orbits of the Anosov flow, the associated Lagrangian cylinders in the Fukaya category are non-isomorphic. So we do get a lot of non-isomorphic objects, which is nice. But this orbit category is not finally split generated. And moreover, it's not homologically smooth. So homological smoothness is a very nice property that says that, well, the definition is that the diagonal bimodule is split generated by unit modules. So, I mean, if you don't know what it means, it's not very relevant, but I should say that for Weinstein domains, it's known that the wrapped Fukaya category is homologically smooth. And so this situation is extremely different from the Weinstein situation. But I should say that even though the orbit category itself is not homologically smooth and not finally split generated, it's still possible that this whole collection of objects, this whole collection of Lagrangian cylinders of the simple closed orbit, they might still split generate the whole Fukaya category. And that actually we don't really know. If they do, that would give the first example of what's called a degenerate Liouville manifold. So essentially a Liouville manifold whose Fukaya category is not homologically smooth. But if this orbit category does not split generate the whole wrapped Fukaya category, that would mean that there are more Lagrangians that we are not quite able to see. And I think it would be a bit surprising, but probably proving that this orbit category split generate the wrapped Fukaya category, that should require new techniques that what is currently known and the techniques of Ganatra and Schende, for instance, don't seem to apply and don't seem to say anything interesting in that case, unfortunately. Okay, and I think I'm going to stop here. So thank you for your invitation.
All right, thank you, Thomas, for the very interesting talk.
Thanks.
Any questions?
So can you describe this Lagrangian torus associated to geodesic gamma, exact Lagrangian torus, which you mentioned at some point?
Yes. So where is it? Yes. So I mean, there are different ways of seeing it. I can give you a not very appealing way, which is the following. Take the positive corner lift of the geodesic. That's a Lagrangian cylinder in R cross M, and you can disjoint from itself by pushing it by some Hamiltonian flow, and then on one hand you can wrap it a little bit to create an S1 intersection, and on the pre-quantization end you can wrap it the other way to create another S1 intersection, and then you can try to resolve these two S1 intersections. But that's a not very explicit point of view. There is a better point of view, which is much more explicit, but that involves some computations, which is to write down the McDuff Liouville form in coordinates near this geodesic, and try to write an equation or parameterization for this Lagrangian. It roughly looks like this blue circle rotated along gamma, but not quite, because the projection on if I have coordinates r, which is or t is the parameterization of the orbit and r is the other coordinate, then essentially this Lagrangian will wiggle in this r direction, and the way it wiggles depends on one of these two coordinates in the fibers. Yeah, I don't know. I think maybe the best way is just to see the parameterization and look at the equation which is in the paper. But yeah, it roughly looks like that.
Thank you.
And maybe I should also say that, so this first construction by this cylinder that I wrap in both hands suggests that this Lagrangian torus is split generated by the cylinder, because it's geometrically obtained by some surgery. But unfortunately, it's an S1 surgery, so we don't really know if that would give a cone or a twisted complex in the Fukaya category, but at least geometrically, they are obtained by these Lagrangian cylinders, and so we don't expect this Lagrangian torus to be a new object in the Fukaya category. It should just be some cone over the cylinder associated to this geodesic.
Yeah, I don't know if you mentioned it because my internet kicked me out, but that will require some sort of like S1 equivariant version of full Torus surgery realized as a cone in the Fukaya category. Any other questions or comments? Okay, in that case, we thank the speaker again. So thank you, Thomas, for the wonderful talk, and thank all the other speakers that came before again.